Hi, welcome to the session. In the last session, we had a discussion on transformer operation on no load. Now, in this session, we will be discussing about transformer operation during load. So, this session is going to be very important. If you can understand this one, definitely you can able to answer the question maybe in any examination, whether it is GATE or ESC or PSU examination. Okay, so this is very important. Lot of conclusions we are going to take up in this one. Okay, so let's see here operation and equivalent circuit also. Operation and equivalent circuit. Operation on load. In the last session we have discussed operation on no load condition. Okay, I did not draw the equivalent circuit on no load, but let me show you the equivalent circuit on no load condition also, and so that you can understand. Okay, so the equivalent circuit on no load, it will be like this. Okay, what we have done, under no load the current is very small. Under no load the current is very small, as I naught is very small. You don't get copper losses, you don't get much copper losses. That too, this I naught is going to be circulated only in one winding, other winding is not carrying any current. Okay, as this is very small, the copper losses are going to be very small. Okay, so that means what? No need to represent the winding parameters, no need to represent the winding resistance, no need to represent the winding reactance parameters. It is enough to represent only core parameters. We have seen already the core parameters, that is magnetizing current, reactance X naught and R naught, that is magnetizing current and working component of current. So as a working component of current and magnetizing component of current are not of same magnitude, how we have to draw them? We have to draw the currents, as the current magnitudes are not same, we have to draw their components in parallel. If the currents are same, we have to draw R naught and X naught in series. As the currents are different, as the current magnitudes are different, R naught and X naught should be in parallel. So I can get here R naught and X naught like this. So R naught and X naught like this. Okay. So now the current is what? The current is here magnetizing component of current, and here the current is working component of current. Who will drive the current? Voltage, source voltage only. So I can keep the voltage source across this one. This is the source voltage V of t. This is the source voltage V of t. And the combination of these two currents is going to be I naught. Now if you want me to represent the current, if you want me to represent the winding, let me show you the winding here. Okay. Actually this I naught is flowing through the winding only. Okay, but I am just representing this core parameter. Okay, even though there is a current flow through the winding, it creates a very small amount of copper loss, and that's the reason why we are not representing the winding resistance and reactance. We are just neglecting them. And another side low voltage winding is just an open circuit. Because of an open circuit, the current is zero, and we are not considering the secondary winding parameters also. So this is the equivalent circuit of a transformer under no load condition. If you see from the equivalent circuit, I can write here it as working component of current can be taken as simply V divided by RW. Okay, working component of current can be taken as V divided by R naught. Okay, R naught is the core loss component, or that is going to represent the core loss, iron loss, right? And magnetizing component of current can be taken as V divided by X naught. According to Ohm's law, I is equals to V by R. Okay, if you want to write Jx naught, you can write Jx naught also, no issues. Jx naught ohms and R naught ohms. Okay, so this is the equivalent circuit of a transformer under no load condition. I am not representing any load here because, I am not representing any core here because the core branch parameter is represented. This is the core nature. Okay, these are core branch parameters. Okay, all right. Now let us move on to the transformer operation on load, and we will see the same kind of equivalent circuit, the operation and all those things. Okay. So before the same theory I am going to explain here. I am just adding a sheet here. Let me take up the transformer here. Please listen carefully. It's very, there are so many important conclusions are going to be made here in this operation. Okay. So please be careful and try to understand the points, each and every point. Alright. So on this side I am going to place high voltage winding, and this high voltage winding is connected to a voltage source like this. Of course, if you want to give a supply, you can give supply. This is my supply voltage V. Right. The supply voltage is going to drive the current I. First current is what? Magnetizing component of current. So I am representing magnetizing component of current. What it will do? It will create the flux lines. It will create the flux lines. What is that flux lines? Phi m. Okay. Let me show you phi m here. And what is the direction of phi m? The direction of phi m is like this. I am representing the direction of flux lines is like this. This is not a phasor notation, direction I am representing. Okay, I am calling this as N1, and the induced EMF can be taken as E1. What will be the polarity? EMF will oppose the very cause of its production. We have seen already. So the EMF is going to oppose the source voltage. If the source polarity is positive, EMF polarity is also positive. I can take up this as a dot and it will be negative. Okay, even on the secondary side also, I can represent here. Even on the secondary side also, I can represent. This is N2. Let me represent this as LV and let me represent this as HV side. Because more number of turns, HV, less number of turns, LV. Low voltage winding and high voltage winding. Okay. Now here also, as a flux is linking with the conductors, an EMF is going to be induced here also. Okay, we have seen in the no load operation, the secondary EMF cannot satisfy the Lenz's law, whereas the primary EMF is able to satisfy the Lenz's law. Okay, and one more thing here, when the magnetization is happening, one more current is flowing. What is that current? That current is working component of current. The phasor sum of these two currents is called as no load component of current. The phasor sum of these two currents is called as no load component of current. So magnetizing component of current is to create the magnetic field. Working component of current is going to create the supply the losses which are existed in the iron, which is hysteresis losses and eddy current losses. Okay, right. So the phasor sum of these two currents is no load current. So this is what no load operation we have seen. This is what no load operation. And now if you see the load operation, I am going to connect a load here. Maybe I am taking it as a lagging load. Let me take up it as simply R1 X1, or let me take up it as RL XL. Okay, I am connecting this load, lagging load, to the second coil. I am connecting the lagging load to the second coil. The moment when you connect the load, what is going to happen? This EMF has a closed path now. The EMF has a closed path now. The potential difference can drive the current through the closed path till the load is closed. If the load is not closed, no current, no closed path, so no current flow. And now here the current starts flowing. In which direction the current has to flow? The direction of current in such a way that it should produce a flux to oppose the very cause of its production. The cause for the production of EMF is mutual flux line. So to oppose the mutual flux line, the EMF has to drive a current and it has to set up a flux line in the opposite direction. Let me show you like this. This is the phi 2 direction. I am not drawing completely. So you can assume that this phi 2 will be like this, in opposite to phi m. So let me show you here. If I take up the waveform will be like this. Okay, if this is phi m waveform, now for this phi m waveform, opposite to phi m waveform, here phi 2 waveform will be established like this. So this is my phi 2 waveform. Okay, because it is to oppose, it has to oppose. When phi 2 is going to be set up, now definitely this is going to be opposed and lens law is going to be satisfied. Now to produce a flux in the upward direction, what should be the current direction in the secondary side? If you are expecting a flux in the upward direction, the current has to flow like this. The current has to flow like this. Okay, it has to enter here, come out like this. It has to enter here. So that means what? Backward it should be right to left, and front side it will be like this. So it has to enter here, leave like this. It has to leave like this. And you see on the front side the current has to be like this. The current has to be like this. Okay. So here the current is leaving from this terminal. This is my I2 current. This is my I2 current. You can take it as capital I2 or small I2, doesn't matter. As a current is leaving this terminal, this EMF is like a source. Okay, this EMF is like a source. Now the N2 coil is like a source, is like an active element. It is delivering the current to the load. So therefore the current leaving terminal will be positive and entering terminal will be negative, and this is the dotted terminal. You see the polarity of induced EMF, the polarity of E2 and the polarity of E1 is same as V. They are opposing the sources. They are opposing the sources to satisfy the Lenz's law. Okay, so here I2 is flowing and setting up the flux in opposite to phi m direction. So when phi 2 is opposing the phi m, now the net flux is going to come down. If the net flux comes down, here, what I can say, if the net flux comes down here, what will happen? The induced EMF also going to be reduces. Here the induced EMF is going to be reduces. If the EMF is going to be reduces, now potential difference is going to be increases. Let me show you one example. If I take up the initial voltage as 200, okay, initial EMF as around 190, the potential difference is around, let me take up it as 198, okay, the potential difference is around 2 volts. So 2 volts is a potential difference which is driving I0 current, of course, and that I0 current has IW and I mu. This is what which is happening. Now the moment when the load is closed, the moment when the load is connected, I2 is flowing, that I2 is setting up the flux phi 2 and phi 2 is opposing the phi m. So therefore it is resulting in reduction in flux. As a flux is reduced, now EMF will reduce. It might come down to 185. Maybe some value, I am just assuming. If it comes down to 185, what is the potential difference now? Earlier the potential difference is just 2 volts. According to the 2 volts, only I0 is flowing. Now potential difference is around 15 volts. Okay. Now the potential difference is around 15 volts. Now because of increase in potential difference, now there will be one more current to flow, that is we call it as I1 dash. Along with this I0, there will be an extra current. There will be a new current flow because of this increase in potential. Now, what this new current will do? This I1 dash current is going to set up. a phi 1 dash flux. This I1 dash current is going to set up phi 1 dash flux, which is opposite to phi 2. So let me show you in the waveform also here. So as phi 2 is opposing the phi m, net flux is reducing, EMF is reducing. As EMF is reduced, potential difference is increasing. This potential difference is driving an extra current. This is driving one more current, and that current is setting up a phi 1 dash, which is opposite to phi 2 to satisfy the Lenz's law. So I can draw phi 1 dash like this. This is my phi 1 dash. Now phi 1 dash, what I can say, now phi 1 dash and phi 2 can be compensated. Phi 1 dash and phi 2 can be compensated, and the net flux again becomes mutual flux again, phi m only. Because phi 1 dash is opposing phi 2, and therefore they are going to be compensated, and the new available flux is phi m only. Let us see once again with one more load. I am connecting one more load here. One more lagging load. Okay, if I connect one more lagging load RL and XL, what is going to happen? The equivalent impedance of the load will decrease now, because I am connecting one more load in parallel. The equivalent impedance will be less than the lesser value. As the equivalent impedance decreases, now this current will increase. I2 component will increase, load component of current will increase. If the load component of current increases, phi 2 will increase. That means what? This N2 into I2 will increase. Magnetomotive force produced on the secondary side will increase. More magnetomotive force will be increased. More magnetomotive force will be produced. That means what? This phi 2 is opposing the mutual flux again. Again net flux will come down. If the net flux comes down, EMF comes down to a value maybe 160. Maybe 160. Now the potential difference is how much? 200 minus 160, it will become as 40 volts. Earlier the potential difference is 15, because of 15 I1 dash is flowing, and now the potential difference is 40, because of 40 volts I1 dash magnitude will increase. Why? To satisfy the Lenz's law. Now as I1 dash magnitude is increasing, then definitely phi 1 dash is going to be increases. So I1 dash will circulate in N1 in N1 turns, and it will set up a huge magnetomotive force at the primary side also, so as to compensate the secondary magnetomotive force. So now this phi 1 dash and phi 2 will again compensate. Again net flux will become the mutual flux. Because when load component of flux, source component of flux, both are opposing and cancelling, what is available? Only phi m. You keep no load, you keep half load or 1/4 load or any load. From no load to any load, the flux in the transformer core is only the mutual flux. Phi m. So I can say that from no load to any load, the flux in the transformer core is constant. That is the reason why we call the transformer as constant flux device. Transformer is a constant flux device. From no load to any load. Here the first point, please remember, from no load to any load. From no load to any load, the flux is constant. Therefore, we call transformer as constant flux device. Okay. Now let us see one more conclusion here. I am saying that the magnetomotive force produced at the secondary and the magnetomotive force produced at the primary are equal and opposite manner. They are cancelling. Okay, they are cancelling. So here I am saying that phi 2 and phi 1 dash, they are equal and opposite manner. How can I write that? Phi 2 and phi 1, MMF by reluctances. The reluctance at this side, secondary side, second leg, the reluctance at the first leg, and the reluctance offered by the entire core is same, na? If the reluctances are same, MMFs are same. If MMFs are same, fluxes are same. Okay, so I can write here the next point here. Phi 2 is equals to phi 1 dash. Phi 2 is equals to phi 1 dash. Okay, how can I write phi 2? MMF 2 divided by reluctance 2. Phi 1 dash MMF 1 divided by reluctance 1. Okay, here the reluctances are same. The reluctance offered by the entire core is going to be same, whether it is at secondary or primary, it is same, na? So MMFs are same. If I equate the MMFs, how can I write MMFs? MMF2 can be written as N2 into I2. Okay, yeah, how can I write MMF1? N1 into I1 dash. Let me write this one, N1 into I1 dash, because not actually I0. I0 is not creating the MMF phi 1 dash current. So that's phi 1 dash flux. So I am not including I0. So MMF 1 is due to I1 dash current. So that is N1 into I1 dash. Okay. So this N2 I2 is equal and opposite to N1 I1, or otherwise whatever the magnetomotive force which is produced at the secondary, that can be compensated by the magnetomotive force produced by the primary. Okay, that's the reason why we call it as transformer is a constant flux device, and here MMF is balancing. Magnetomotive forces are balanced, equal and opposite. The net force acting on the core the net force acting on the core is 0. The net force acting on the core is 0. So therefore what I can write here, N2 minus N1, N2I2 minus N1I1 dash is equals to 0. Net force is 0. If net force is 0, I can say that transformer cannot move in any one side. Transformer is going to be stationary like this. Transformer is a stationary device. Why? Why it is stationary? Because whatever the force which is produced here, there will be an equal and opposite force from this side. As there is an equal and opposite force from this side, transformer is not experiencing any force. If this is my one side and this is one other side, I am applying a force here, I am applying a force here. If this force is greater than this force, then core can move on this side. If this force is greater than this force, then the core can move on this side. If both forces are equal and opposite, core cannot move anywhere. Transformer is a stationary device because magnetomotive forces are equal and opposite. The net force acting on the core is going to be, the net force acting on the core is going to be 0. The net force acting on the core is going to be 0. Therefore we can call transformer is a constant. Therefore transformer is stationary. Transformer is stationary. If N1I1 is not equal to N2I2, if N2I2 is not equal to N1I1 dash, then the transformer would have moved. If N2I2 is not equals to N1 into I1 dash, then it is no more, then transformer will be a moving device. Then transformer will be a moving device. The transformer will be a moving device. And we know this, here, the point N2I2 is equals to N1 into I1 dash. We got it, na? We got this point, na? We know that here in the operation we have seen I naught and I1 dash. The combination of these two I can write it as I1. This is a total primary phasor current. The primary phasor current is I1 dash plus I naught. I naught is very small, na? I naught is very small. So here, if you can add I naught to the I1 dash also. N1 I1 I am writing. So I1 dash plus I naught, I1 dash plus I naught is going to be I1. Even though I am adding, it doesn't matter. Okay, even though I am adding, it doesn't matter. Okay, it's very small, so negligible, very small, negligible. Add it, no problem, negligible. We know during the EMF equation I said EMF per turn is equal. EMF per turn on both the sides are equal. We know that E1 by N1 is equals to E2 by N2. Or else I can write it as E1 by E2 is equals to N1 by N2. From this one I can write it as E1 by E2 is equals to N1 by N2. Okay, what can I write from this one? N1 by N2 is equals to I2 by I1. N1 by N2 is equals to I2 by I1. Yes or no? N1 by N2 is equals to I2 by I1. Okay, this is what, na? Magnetomotive forces are equal and opposite. So now I can take up, if I can cross multiply this E1 and I1, now I will be getting E2 I2 is equals to E1 I1. What does it mean? This is the power received by the secondary and this is the power at the primary. The power at the primary and the power at the secondaries are equal. In a transformer, whatever the power received by the primary, that will be transferred to the secondary. So secondary is receiving the power from the primary without any loss. The power received by the secondary is equal to power transferred by the primary. That is the reason why we call it as transformer. Transformer is a constant power device. Constant. By the way, this is not active power. This is an apparent power. Constant apparent power device. Yes, constant apparent power device. Not active power, not reactive power. If you multiply E2 into I2 into cos theta, that's active power. E1 into I1 into cos theta 1, that's a primary power. Not active powers. Okay, I have not represented any cos components. I have represented only voltage and current. Voltage and currents. Okay, so here I can say that transformer is a constant power transfer device, apparent power transfer device. So I concluded one thing: transformer is a constant flux device. Transformer satisfies the in transformer the magnetomotive forces balances are equal and opposite. Then only transformer can become a stationary device. Otherwise, it will be moving device. And one more conclusion is transformer is an apparent device, apparent power device. Okay, so here these things are done. Okay, if you see here, let me draw the phasor diagram. Let me draw the phasor diagram. Okay, if you draw the phasor diagram, how it looks like, let's see. And one more point I wanted to say: whatever the rate of change of flux linkages happens here, the same rate of change of flux linkages happens here. That means what? Here one flux, same phi m only, same phi m is linking here, same phi m is linking here. The rate of change of flux linkages with respect to both the coils is same, and hence the frequency at which it is going to induce, the frequency at which the EMF is going to be induced is also same. Okay, the frequency of induced EMF, the frequency of induced EMF in the secondary, the frequency of induced EMF in the primary is same as the supply frequency. Why? Because whatever the change which is happening here, that is due to what? Due to the current change. Current change is due to what? Supply change. Okay, whatever the change is here, the same change will happen here, the same change will happen here. That means I can say transformer is a constant frequency device. Okay, transformer is a constant frequency device. If I add here the rate of change of flux linkages N1 into d phi by dt and E2 at E2 also N2 into d phi by dt. Okay, here the rate of change d phi by dt, this is same. Rate of change of linkage of flux lines is same with respect to N1 and N2. Therefore, the frequency of induced EMF, is same as supply frequency. The frequency of induced EMF is same as supply frequency. Why same as supply frequency? Because this d phi by dt is variation with respect to supply current. The supply current is because of supply voltage. So whatever the frequency will be there for the supply voltage, same frequency will be there for EMFs also. Therefore, I can call it as transformer is a constant frequency device. Transformer is a constant frequency device. It's very, very important. Okay, so let me put all those points. Transformer, constant flux device. Constant flux doesn't mean the time invariant. Constant means from no load to any load. Constant means from no load to any load. Constant means from no load to any load. Now, transformer is a constant apparent power device, S device. Okay. Now, the next point, transformer satisfies a magnetomotive force balance. MMFs, magnetomotive force, the net force I can say that the net force acting on the core is 0. That's the reason why transformer is a stationary device. Transformer is a stationary device since the net force is going to be 0. N2I2 is equals to N2I2 minus N1I1 is equals to 0. Equal and opposite forces. And the next point is here, transformer is a constant frequency device. Okay, these are very, very important conclusions. Please try to remember. So they'll give you the options, 4 to 5 options. Which of the following is correct for about the transformer? Transformer is a constant apparent power device. Transformer is a constant frequency device. Transformer is a constant flux device. Transformer is a stationary device. All are correct. Okay, all right. They'll give you transformer is a rotating device. It is not a rotating device because it is not moving. It is not moving. So let me show you. Here the phasor diagram. So if you want me to draw the phasor diagram will be like this. The phasor diagram will be like this. So here the supply voltage, and this side I am taking magnetizing component of current, and on this mutual flux. Okay, so here working component of current, and this is going to be your no load current I naught, and we know that this is going to be theta naught. Okay, theta naught is the no load power factor angle. Please try to remember, theta naught is a no load power factor angle. No load power factor angle. Okay, right. Now, I need to draw the EMFs. I am assuming the EMF polarity is opposite to source polarity. I am assuming the EMF polarities as opposite to source polarities. Okay, if I assume the EMF polarities as opposite to source polarities, then I can draw E1 like this, because N1 is large number of turns, so E1 is greater than E2. E1 is greater than E2. So this is high voltage winding and this is low voltage winding. Okay, let us assume for time being, I am not drawing the winding drops and all those things. That is, we have got it now. Current is flowing now. In this current is flowing now. Now load component of current is also flowing, not just a small current. Along with that, load component of current is also flowing. So when the current is increasing, you need to consider the drops also. I will consider the drop later. So if you consider the drops, then the phasor diagram will be very clumsy. Without considering the drops, let me show you. Okay, let us assume for time being E2 is almost equals to V2. The terminal voltage is almost equals to V2. Actually, it will not be. Terminal voltage will be less than the induced EMF, because EMF will be generated and it will be dropped, and then later voltage will be available. Alright. So here V2 is approximately equals to E2, I am assuming. As a load is lagging load, let me draw the current here. The current lags the E or V2 or E2 by some angle. What is this current? This angle is theta 2. Theta 2 is the load power factor angle. Theta 2 is a load power factor angle. Okay, you can take up, if it is lagging load power factor angle. If it is leading load power factor angle. If I2 is flowing like this, if I2 is lagging like this, in the same phase you will be having phi 2 na. Because I2, whenever I2 is going to be circulated in the N2, then you will get magnetomotive force, you will get flux establishment phi 2. Now this phi 2 is going to oppose phi m. Therefore net flux comes down, EMF comes down, and the potential difference increases. Therefore one more current flows. The source will drive one more current. What is that current? I1 dash. So the I1 dash current will be like this. I1 dash current will be like this. Okay, so this is my I1 dash current, and I1 dash current will set up phi 1 dash flux. What is the angle between V and I1 dash? Theta 2. The angle between V and I1 dash is theta 2. Okay, now this I1 dash and this I1 dash and I naught together, the phasor sum of these two is going to become equals to the total primary current. So let me add up these. So this is the total primary current. Yeah. Now the angle between supply voltage and supply, this is the supply current. The angle between supply voltage and supply current is theta 1. So theta 1 is the primary power factor angle. Theta 1 is a primary power factor angle. Theta 2 you can take up as secondary power factor. Theta 2 is a secondary power factor. Theta 1 is a primary power factor angle. Now you see, you look at the angles and tell me which is greater. Theta naught is much more greater, and theta 1 is greater. Then theta 2 is very, very smaller. So by observing the phasor diagram, I can say theta naught is greater than theta 1. Theta 1 is greater than theta 2. Cos of large value is a small value. Cos of 90 is 0. Okay, cos 0 is 1. So if the angle is less, cos value is more. If the angle is more, cos value is less. So I can write here cos theta naught is going to be less than cos theta 1. Cos theta 1 is going to be less than cos theta 2, which means no load power factor is poor. No load power factor is poor, and load power factor is good. Load power factor is good. Okay, yes or no? If no load power factor is 0.2, then primary power factor is maybe 0.4 or 0.5. Secondary power factor will be maybe 0.7 or 0.8. like that. If this is 0.2, this could be 0.8, 0.5 or 0.6, and this could be 0.7 or 0.8, like that. Okay, you see here, as the power factors are not same, you cannot take up the active powers are equal. You cannot take the active powers as equal. You cannot take up active powers as equal. Okay, so here let me write here P1. So P1 can be written as E1 into I1 into cos theta 1. This is the primary active power. Okay, we can write P2 as P2 can be written as E2 into I2 into cos theta 2. This is a secondary active power. Here E1 I1 is equals to E2 I2. Apparent powers are equal but not active powers. Why? Because cos theta 1 is not equal to cos theta 2. As cos theta 1 is not equals to cos theta 2, we can say therefore P1 is not equals to P2. Similarly, if cos thetas are not equal, sin theta is also not equal, na? Sin theta is also not equal. So sin theta 1 is not equals to sin theta 2. Therefore Q1 is not equals to Q2. E1 I1 sin theta 1, E2 I2 sin theta 2 is also not equal. Reactive powers are not same on primary and secondary. Active powers are not same on primary and secondary. You know why? You see the transformer diagram. Here, this secondary winding will deliver the active power demanded by the load, reactive power demanded by the load. Secondary winding will deliver the active power demanded by the load, reactive power demanded by the load. But source has to deliver the active power demanded by the load, has to deliver the reactive power demanded by the core. The source has to deliver the active power demanded by the primary winding, core and load. Yes or no? The load has to deliver only this much power, but source has to deliver entire, na? How can you expect the same amount of angles? How can you expect the same amount of phase angles? The phase angles are not going to be same. Therefore, we can say that transformer is not a constant active power device. Transformer is not a constant reactive power device, but transformer is a constant apparent power device. So there is one more point I wanted to say. What is this I1 dash? I1 dash is a primary source component of current. How can I relate with the I2? We got it as N2 into I2 is equals to N1 into I1 dash. This is the MMF balance equation. Now I1 dash I can write it as N2 divided by N1 is equals N2 divided by N1 into I2. What is this N2 by N1? E2 by E1. Okay, so here we have got it as EMF per turn E1 by N1 is equals to E2 by N2. Na? From this we can write it as E2 by N2 is equals to N2 by N1. We call this as transformation ratio. Okay, K we represent. Some textbooks represents with A, some textbooks will represent with K. No issues. Okay, E2 by E1. E2 is the secondary voltage, E1 is the input voltage, like V2 by V1. Okay, N2 by N1 is equals to K. Not turns ratio. Turns ratio is simply N1 by N2. Okay, please remember turns ratio is N1 by N2. Transformation ratio is N2 by N1. Output by input, it is like a gain. Output voltage by input voltage, it is like a voltage gain. Okay, so here we have got E1 by N1. From this is EMF per turn is same, na? 4.44 into F into 5 into we got this, na? EMF per turn. From this only we have solved. The ratio is named as E2 by E1, N2 by N1 is named as K. Transformation ratio. Now I can use N2 by N1. I can use this transformation ratio here, and I can write I1 dash is equals to K times I2. I1 dash is equals to K times I2. So that means what? The primary source component of current is K times the load component of current. K times the load component of current. For every load component of current on the source side, K times the source component of current will be there. K times the load component of current will be there. For every load component of current on the primary side, K times the load component of current comes in to compensate, to nullify the magnetomotive forces, to oppose the magnetomotive forces and to nullify, to get net force as 0. I am repeating, for every load component of current, there will be K times the load component of current. K times I2. If it is I2, K times I2. If it is IR, K times IR. If it is IC, K times IC. For every load component of current, there will be a K times load component of current on the primary side to compensate the magnetomotive forces, to get a net force equals to 0, to make the transformer as a stationary device. Okay. So I think with this information we can move on to the problems. So let me solve some problems on the transformer operation, and possibly we can go ahead with the even equivalent circuit also. I will include the equivalent circuit also. After doing 1 or 2 problems, we will discuss about equivalent circuit also. Okay. At this point, I wanted to clear one more point. That is, transformer is not constant active power, not constant reactive power. But how can you make the transformer as constant active power, constant reactive power, constant apparent power? If thetas are equal, then I can make transformer as constant power, active power, constant reactive power, constant apparent power. How can you make thetas as equal? Okay, to get P1 equals to P2, comma, Q1 is equals to Q2, and S1 equals to S2, we need to get primary power factor angle, secondary power factor angle must be same. We must get theta 1 equals to theta 2. How is it possible? Theta 1 equal to theta 2 is possible only in ideal transformer, because no losses. If there is no loss, theta 1 equal to theta 2 is possible. Theta 1 equal to theta 2 is possible in ideal transformer. Okay. In ideal transformer, no losses, no losses means here working component of current is 0 and magnetizing component of current is also 0. If both are 0, no load current is 0. Now how will be the phasor diagram? You see the phasor diagram how it looks like. The phasor diagram, this is the voltage and this is going to be the flux. You cannot represent magnetizing component of current. You cannot represent working component of current, and there is no load current. What will be there if I draw the EMFs? If I draw the EMFs here, EMFs on the downward side, E1, E2. Now the currents will be like this. The current is lagging with respect to voltage. This is theta 2. Okay, and we get here it as phi 2. Okay. For every load component of current, there should be a K times the load component of current. There should be a K times the load component of current on the primary side. So K times I2. What is this? I1 dash. Okay. What is the angle between E2 and I2? Theta 2. What is the angle between V and I2? The same. V and I1 dash, the same angle you will get. So this is theta 1. Is it not the primary phasor current? This is the primary current. I1 dash is the current which is flowing on the primary winding. Okay. Earlier it was I1. Now it is just I1 dash. Why? Earlier I1 dash, along with I1 dash, I0 is also there. Now here I0 is not there. Therefore you can say only theta 1. Okay. Now here theta 2, theta 1, primary power factor angle and secondary power factor angles are same. Okay. If this is 20 degrees, this is also 20 degrees. If this is 30 degrees, this is also 30 degrees. Now here, so primary power will be simply E1 into I1 dash into cos theta 1, E2 into I2 into cos theta 2. Active powers, reactive powers, all are equal. As angles are equal, active powers, reactive powers and apparent powers are equal. That's the reason why transformer is a constant ideal transformer is a constant active power device, constant reactive power device, constant apparent power device also. This is not possible in ideal case. This is not possible in practical case. Okay. So that is the point I wanted to clear here, and whatever the points so far we have discussed, that information is given here in terms of theoretical points. Okay. So N1, this is N, it's like N1 I1 dash load component of primary MMF, okay, to satisfy the lens law and all those things I have represented here in the form of 1 by 1. Now can you answer this? Can you answer this? If the load power factor transformer is, if the load power factor of transformer is 0.8 lagging, then its primary power factor is, load power factor is 0.8. What will be the primary power factor? Just now we have seen, no load power factor is very much less than the primary power factor. Primary power factor is very much less than secondary power factor. If this is 0.2, this will be approximately 0.5 and this will be maybe 0.8. He said load power factor. This is load, na? This is secondary power factor or load power factor, and this is primary power factor, and this is no load power factor. So if the load power factor is 0.8, then primary power factor definitely less than 0.8 only, no? Definitely less than 0.8. You should not get more than 0.8. You should not get more than 0.8. You should get less than 0.8 only. So option C could be the correct answer. Okay, option C could be the correct answer. Let us move on to the one more example here. I have a transformer. Which is the rating of around 100 kVA. Okay, a 100 kVA 2400 by 240 volts 50 Hz single phase transformer has an exciting current of 0.64 amperes. Generally, if he has given exciting current, which means no load current, most of the times they will represent magnetizing current. Otherwise, you take up it as if they don't represent it as magnetizing current, you just take it as no load current only. Exciting current means no load current, I naught. Don't take up it as magnetizing current. Okay, I naught exciting current of 0.64 amperes and core loss of 700 watts Wi. Okay, when its high voltage side is energized at rated voltage and rated frequency, if the current is 40 amperes at 0.8 power factor lagging on the LV side, then the magnitude of the primary current will be. So let me show you the simple transformer structure here. Okay, if you look at the transformer, it will be like this. This is of 2400 by 240 volts transformer na. Okay, so this is HV and this is LV. Okay, now HV is excited with what? HV is excited with, high voltage side is excited with rated voltage and rated frequency. That means what? I have to connect 2400 50 Hertz. Rated voltage and rated frequency. Rated frequency means designed frequency. Rated voltage means designed voltage we need to apply. So rated voltage and rated frequency I have given, high voltage side. Alright. Now on the secondary side he said if the load current is 40 amperes at 0.8 power factor lagging. Now let me show you here load. If the load current is 40 amperes and the power factor of the load is 0.8 lagging, then what is the magnitude of primary component of current? What is the magnitude of primary component of current? What is I1? He is asking. How do you calculate I1? I1 is equals to no load current plus load component of current. K times the load component of current. Okay, I1 is equals to no load current plus K times the load component of current na. So you need to calculate, no load current is already known, exciting current, that is 0.64. That is 0.64. Okay. Now you need to calculate just load component of current. You need to calculate just a load component of current. So how do you calculate load component of current? I2, how do you calculate? I2 can be calculated from, of course, I2 also given here 40. The secondary current also he has given 40. Okay, but you need to take care of this angles. Be careful, they are not arithmetic sum, they are vector sum. So please be care about the angles. So I2 at an angle of what? 40 at an angle of cos inverse of pi. I2 magnitude we know and the phase angle you need to calculate. 40 at an angle of cos inverse of 0.8. This is the angle at which the current flows na. So cos inverse of 0.8 will be 36.86. So 40 at an angle 36.86. How can I write? As it is a lagging load, I have to write it as minus 36.86. Be careful. It is minus 36.86. So this current lags with respect to voltage by minus 36.86. Which voltage? Secondary voltage or secondary EMF. This load current lags the load voltage with respect to this load current lags the load voltage by minus 36.86 degrees. Okay, I have got this I2 magnitude. I want K times now. I want K times. So this is nothing but I0 plus I1 dash, which is nothing but what? I0 plus I1 dash. So now I1 dash can be taken as K times I2. K times I2. What is K? K is the transformation ratio, N2 by N1. K is N2 by N1 or E2 by E1 into I2. So N2 or E2 can be taken as 240 divided by 2400. 240 divided by 2400 into I2 is a 40 at an angle minus 36.86. Okay, so if you solve this, 240 divided by 2400, it comes out to be 1 by 10. So 40 by 10 will be 4. So 4 at an angle minus 36.86. Okay, so this is the primary component of current. So the primary component of current is going to lag with the supply voltage by minus 36.86 degrees. Okay, minus 36.86 degrees. I said na, here, if you look at the phasor diagram, theta 2, this is the load current minus 36.86, and here this I1 dash is also going to lag with same angle, 36.86 degrees only. So with respect to V, I1 dash is going to lag with respect to 36.86 degrees. Okay, now I have calculated here I1 dash, then I need to calculate I0. I0 we know, but we do not know the phase angle. To know the phase angle, we need to calculate theta naught. We need to calculate theta naught. How do you calculate theta naught? How do you calculate theta naught here? He has given iron loss component. He has given iron loss component, that is Wi. What is a Wi? You can write it as Wi is nothing but iron loss, which is going to be dissipated in the R naught. Okay, so I can write here iron loss component as supply voltage into current. That is what current? I naught into cos theta naught. I naught into cos theta naught. Do we know this? Yes, we know no load current, we know the supply voltage also. Now you can calculate this cos theta loss. This is iron loss, I can say. How can you say that this is iron loss? Because working component of current, na? Who is going to create the loss? Working component of current only. How do you write a working component of current? Working component of current is equals to I naught into cos theta naught. Okay. Now from this I can calculate cos theta naught. So Wi divided by V into I naught. What is Wi? He has given the wattmeter iron losses as around 700, and the voltage, where we are applying voltage? On the high voltage side, 2400 into I naught is how much? By the way, he has given I naught as around exciting current as around 0.64 amperes. Okay. So if you take up this one, you will get the power factor, cos theta naught. Now from this, you can calculate theta naught. Now add that theta naught to I naught. So can you tell me what could be the possible answer here? If you calculate 2400 into 0.64 and 700 divided by this answer, I am getting it as around 0.45. So 0.455 lagging. Okay. Now cos inverse of this answer 0.44y lagging will be around 62.8 degrees. So I can represent I naught with 0.64 at an angle of minus 62.88 degrees. Now if you draw the phasor diagram, you will understand. You see the phasor diagram. This is my supply voltage, and this is my magnetizing component of current, this is the mutual flux, and this is the working component of current. Now this is the no load component of current. What is this theta naught? What is this theta naught? 62.88. Theta naught is 62.88. I am not writing over there. I am just writing. So see, we got it as minus. With respect to voltage, the current lags. Okay. Now we have got induced EMFs also. Okay. Let me take up it as high voltage side EMF is this much, E1, and low voltage side EMF is E2. Okay. Now these are the EMFs. So we are connecting a load on the secondary side. What is the load? Lagging load. What is the load? Lagging load. Let me draw the lagging current here. The current lags the secondary voltage by how much angle? He has given power factor as load power factor as 0.8. Cos inverse of 0.8, we got it as 36.86. So with respect to voltage, the current lags by 36.86. Let me write it as theta 2. So theta 2 is 36.86 degrees. Of course, it is lagging. I2 is lagging with respect to voltage. Alright. Now, this I2 is going to set up the flux phi 2. Now, to compensate this one, there should be an opposing current. What is that? I1 dash. I1 dash also same na? 36.86 na? We got it na? What is that I1 dash? K times I2. How much we've got it as? Around 4 at an angle minus 36.86. Okay. Alright. See, the primary component of current to compensate the load component of current is also lagging by same phase angle. Alright. Now the phasor sum of these two. Will be the primary current. I1 dash and I0. The phasor sum of these two currents will be the primary current. So how do you take up the primary current now? This is like one current and this is one more current. It's like, Pythagoras, parallelogram law you can use. F1 square plus F2 square plus 2F1 F2 cos theta you can take up. This is a theta. This is the resultant theta you need to consider now. This is the resultant theta or alpha you need to consider. If you solve it, you will get it. Okay. Let me take up I1 is equals to I0 square plus I1 dash square plus 2 I0 into I1 dash into cos alpha under root. If you substitute all the values, you'll get the I1 magnitude. What is the I0 magnitude? We have got I0 magnitude as 0.64 square. What is the I1 dash magnitude? We got 4. So 4 square plus 2 into 0.64 into I1 dash is 4 and cos of alpha. What is this alpha? Alpha is what? How much you will get? Alpha is theta naught minus 36.86. Alpha is 62.88 minus 36.86. Okay, you will get the answer. Okay, 62.88 minus 36.886. So we will be getting it as around 26.02. Now cos of 26.02. Okay, so please solve the entire term. Cos of 26.02 into 4 into 0.64 into 2. So I am getting this term as 4.6 plus 4 square plus 0.64 square and whole of that root if I apply, I am getting the value as around 4.583. I am getting the total primary component of current as 4.583. Let us check the value of current. 4.583. Yes, it is available or not? Yes, it is available. So this is how you need to do. It's a little bit lengthy calculation, but if you can do all these kind of questions only, you'll understand how the transformer operation is. We will do some more questions on the transformer operation and you'll understand how it will be. Okay, let me show you some more questions also here. A single phase transformer has a turns ratio of 1:2 and is connected to purely resistive load. As shown in the figure. The magnetizing current is 1 ampere. He has given magnetizing current. He did not mention exciting current. Exciting current you take it as no load current I0. The magnetizing current is 1 ampere and the secondary current is 2 ampere. Let me take up it as I2. If the core loss and leakage reactance are neglected, So that means what? Iron loss is equals to 0. Leakage reactance is also 0. Then the primary current is what? So what will be the primary current generally? What will be the primary current generally? The primary current is the combination of I naught and I1 dash. Na? What is I naught? I naught is a combination of working component of current and magnetizing component of current, right? I naught is a combination of working component of current and magnetizing component of current. He has given magnetizing component of current, but he said core loss is 0. If core loss is 0, working component of current is 0, na? This is the current which is going to supply the losses, eddy current and hysteresis losses. So this is 0. Now I can take up, in place of I naught, I can take up only magnetizing component of current. Now in place of I1 dash, I can take up K times I2. Okay, K times I2. So the primary current is equals to phasor sum of magnetizing component of current and transformation times the load current. Load current we know I2. If you can calculate K, you can calculate K times I2. What is K? What is K? K is equals to, it is like N2 divided by N1. N2 is 2, N1 is 1. So K is, I am getting it as 2. Now what will be your I1 dash? I1 dash is equals to 2 times the load current. Load current is how much? 1 ampere. So I am getting it as 2. Now you cannot simply add magnetizing component of current and load component of current simply. You cannot add simply. So the primary current cannot be simply like 1 plus 2. It won't be 3. Okay, 3 is absolutely wrong. 3 is absolutely wrong. How you have to do? You have to do phasor sum. You have to do phasor sum. So in order to the phasor sum, it will be like this. Okay, if you look at the phasor diagram, it will be like this. No, I have a voltage source. This voltage source is going to establish the flux lines by driving the magnetizing component of current. He mentioned it as 1 ampere. Magnetizing current of component, working component of current is 0 because core loss is 0. Alright. Now then, if I take up EMF on this side, maybe E2. Alright. E2 is going to drive the current. What is the load? What is the load? The load is a purely resistive load. If the load is a purely resistive load, the current will be in phase. Okay. Current is in phase. Okay. I2 is in phase with V2 or in phase with E2 since RL load, resistive load, Okay, so this point you should keep it in mind. What is the magnitude of secondary current? The magnitude of secondary current is also 1 ampere he has given. Right. Now for every load component of current, there should be a transformation times the load component of current. No. So quite opposite to this one, we will be having a I1 dash. I1 dash is equals to K times I2. We have calculated already. We got it as 2. Now the phasor sum. If you take up the phasor sum, okay, here is the phasor sum, you see. This is the phasor time. You cannot add 1 plus 2. You have to go ahead with this one. This is I1 now. Now how can I take up I1? I mu square plus I1 dash square plus 2 I mu I1 dash into cos of alpha. This alpha. Yes or no? You take up alpha is how much? Alpha will be 90 degrees. So I1 is equals to I mu square plus I1 dash square plus 2 I mu I1 dash into cos of alpha. Okay, like parallelogram law. What is I mu? We got 1 square. What is I1 dash? 2 square. So 2 times 1 into 2 into cos alpha. Cos alpha is 90 na. If alpha is 90, what is the cos value? 0. So this entire term becomes 0 and you will be having only 1 square plus 2 square. Root of 2 square plus 1 square is root 5. Root 5 will be probably more than 2. Root 4 is 2 na. Root 5 is more than 2. So 2.23 amperes. Probably you will be getting it as 2.23 amperes. You see 2.23 or 2.24, probably you will be getting it as 2.24 amperes. This is one more question on the operation of transformer during the load. Okay, so if that is the question, let us move on to the equivalent circuit also. I hope operation of transformer is clear. Just please remember the I1 dash formula. For every load current, there will be a transformation times the load current on the primary side. I1 dash is equal to K times I2. Okay, if you can represent like that, you can easily solve. And remember, transformer is a constant flux device, constant power device, constant, what I can say, stationary device, all right, constant frequency device also. Okay, right. So let us move on to the another part, that is equivalent circuit. In the no load operation, we did not consider the winding resistance and reactances. But here we can consider the winding resistances and reactances because the current is more now. As a current magnitude, here I2 current magnitude is more. Okay, so I1 dash current is K times I2. This current is more. If current is more, in the winding drop is more. Here also winding drop is more. So you need to consider the winding parameters also. As a current is more, if the load increases, current increases. If the current increases, some amount of leakage flux also increases here. Here also some amount of leakage flux also increases. Okay, so these leakage flux lines are proportional to load currents. Under no load, the I0 is very small. This small current cannot create much leakage flux lines. If the load increases, load current increases. If the load current increases, leakage flux lines will increase. So leakage flux lines are proportional to load current. Leakage flux lines are proportional to load current. Remember this point. Leakage flux lines are proportional to load current. If load current is more, leakage flux line is also more. Okay, if leakage flux lines are more, okay, if the leakage flux lines are more, in this winding, leakage EMF also going to be induced. Na? If this flux is cutting only secondary winding, leakage EMF is also going to be induced, EL2. In this winding, leakage EMF also going to be induced, EL1. Now, if actual EMF is E1, out of that some amount of EMF is going to be leakage. Actual EMF is E2, out of that some EMF is going to be leakage. So therefore, whatever the phasor diagram we have drawn earlier, the phasor diagram is going to be deviated. The phasor diagram is going to be deviated. So in order to get the exact phasor diagram, what we do is, we will assume these reactances. X1 and X2, those are assumed reactances to compensate the leakage induced EMFs. X1 is to compensate EL1, X2 is to compensate EL2. X2 is not the winding reactance, X1 is not the winding reactance of primary and secondary. Okay, X1 is the reactance assumed to compensate leakage induced EMF in the primary. X2 is the reactance which is assumed to compensate the induced EMF in the secondary. Okay, and the resistance R1 is the winding resistance, R2 is the secondary winding resistance. Okay, so here I can add all the drop components. I can add all the drop components. You see here, primary winding resistance and the leakage reactance, and then no load branch component. You can write. Okay, so this I0 and I1 dash together, it will be supply current. I0 and I1 dash together, it will be supply current. On the secondary side, I2 current will be circulating like this side. Okay, so here if you want to solve or if you want me to show you the phasor diagram will be like this. Let me show you the phasor diagram if it is possible. Okay, so the phasor diagram will be like this. This is the voltage source, this is the flux, magnetizing component of current, working component of current, and this is no load component of current. Okay, so we have got, I am not writing the theta naught, no load power factor angle, it's going to be same, and I am writing here the induced EMFs. Primary induced EMF is almost equals to the source voltage. Okay, let me take up secondary EMF as high voltage winding. Okay, let me take up the primary winding as low voltage winding and secondary voltage as let me take up the primary winding as low voltage winding and secondary voltage as, secondary side as high voltage winding. Primary side low voltage winding, secondary side high voltage winding. Okay, now please try to understand. By writing a KVL, you will understand here. By writing a KVL on this side, if you are expecting V1 must be equals to what? I into R1 drop, I into X1 drop and E. So according to KVL, V1 source voltage is equals to I1 into R1 plus J I1 into X1 plus E1 plus E1. So EMF plus this drop is equals to source voltage. How will I get this V1? This is a supply voltage. So to the supply voltage you should add all these drop components. To the EMF you should add all these drop components. Okay. Similarly for the secondary induced EMF. Here terminal voltage V2 is equals to EMF minus resistance drop, leakage reactance drop. So E2 minus I2 into R2 minus J I2 into X2. Okay. So here E2, if I write E2 minus I2 into R2 minus J I2 into X2. Induced EMF minus drop is equal to terminal voltage. Okay. So let us see here. For the induced EMFs, from the induced EMF you have to subtract these drops, then you will get the terminal voltage. Or otherwise for the terminal voltage you should add up drop, resistance drop and reactance drop, I2 X2, then you will get induced EMF. Anything is okay. For the terminal voltage you add this drop, then that will be equals to induced EMF. Okay. Now if you draw the phasor diagram, if you see the phasor diagram, here this is the induced EMF. To get the induced EMF, terminal voltage plus drops will be equal to induced EMF. Now let me show you the terminal voltage here. The terminal voltage and the drops will be little deviated. See, this is the terminal voltage. Let me take up it as V2. Okay, if this is V2, where will be I2? I2 lags with respect to V2 by theta 2, load power factor angle. If I2 is like this, then I2 into R2 component will be, resistance drop component will be in phase with I2. You need to draw in phase, because I2 into R2 voltage drop component, now voltage and current will be in phase in the resistance. Okay, so I have to draw, this is I2 into R2 component. Now I2 into X2 component, perpendicular plus J, perpendicular. So this perpendicular drop, I2 into X2. So V2 plus I2 R2 plus I2 X2 will be the induced EMF. You see, this is the actual load side phasor diagram. Okay, right. Similarly, due to this load current, there will be a K times the load current, and let me draw that. This is my I1 dash, K times I2. Okay, of course this is going to be, you can represent it as phi 1 dash. Here you can write it as phi 2 if you want to compensate. Okay, now here if this is I1 dash, where will be I1 now? The phasor sum of these two. This is going to be the I1 now. This is the primary current now. Now I got primary current. Okay. Now I want to calculate total supply voltage. Supply voltage is equals to what we have got? Supply voltage is equals to EMF plus drops. EMF plus drop. How can I write EMF now? Now project this EMF onto the opposite side. Okay. Let us assume this instead of V, let us assume this as V. Okay. Let us assume instead of V, I am assuming it as I am assuming it as E1. Now for this E1, I have to add resistance drop, reactance drop. How can I add resistance drop in phase with the I1? So this will be my resistance drop, I1 into R1. Now from here, this will be I1 into X1. Now E1 plus I1 into R1 plus I1 into X1. This will be the supply voltage phasor. Okay. Now this is the new power factor angle, primary power factor angle. This is the new no load angle, theta naught. This is the new load angle. There are so many deviations because of leakage components. Because of leakage components. You see, I2 is going to create phi 2, and phi 2 is going to in the same phase. In the same phase, I can draw even leakage flux also. Even in the I1 dash also, here also I can write leakage flux also. Leakage flux on the primary component, leakage flux on the secondary. The EMFs are going to the EMFs. Here I have drawn na. EMFs are lagging with respect to flux. Here also I can draw. Here, this is the leakage flux component on the primary side. So, EMF, the leakage induced EMF EL1 lagging with respect to phi L1. Similarly, leakage flux component on the secondary phi L2. Now, induced EMF is going to lag with respect to, that is, leakage induced EMF is going to lag with respect to the leakage flux line 90 degrees. Here also, it going to lags with respect to flux by 90 degrees. Now these leakage induced EMF components are going to be compensated by this reactance. This assumed reactance, you see, assumed reactance, the secondary reactance on the secondary side, the assumed reactance is this side. You see EL2. Now EL2 is going to be compensated. EL2 is going to be compensated by I2X2 drop component. EL1 is going to be compensated by I1X1 component. EL1 is like this, I1X1 is like this. And when the leakage EMFs are going to be compensated with the reactance, assumed reactances, then you will get again original phasor diagram. Okay, this is actually deviated phasor diagram. If the leakage reactances, if X1, X2, whatever the assumed reactances are there, if they are able to cancel the leakage induced EMFs, then you will not get any much deviation. Okay, so this is the actual phasor diagram we can take up. All right. So coming to the equivalent circuit, that's a phasor diagram, and coming to the equivalent circuit here, I want to tell you one point. As the equivalent circuit has two sides, we need to solve two mesh equations, because it can be 11 kV side, it can be 400 volt side. So two different voltages requires two mesh equations. Same as like superposition theorem. In a circuit, if you have 100 sources, you need to solve 100 times according to superposition theorem. Okay. If you have 10 voltage sources, you need to solve 10 times to get a response. Similarly, here also, as a transformer has two voltages on primary side and secondary side, two different voltages, you need to solve two equations. You think in a power system, so many transformers are there, so many voltage levels are there, so many equations you need to solve. That's the reason why, in order to minimize the number of equations, in order to reduce the time consumption for the calculation, what we do is, we suggest a per unit system, and moreover, we suggest the secondary parameters to primary side or primary parameters to secondary side. We will be transferring secondary parameters to primary side. We will be transferring primary parameters to secondary side. If you are able to transfer this secondary parameters to primary side or primary parameters to secondary side, you will get only one loop equation. So that I can say that loop equations can be done by transferring those secondary parameters to primary side and primary parameters to secondary side. So if you transfer secondary parameters to primary side, this is how you will get like this. We will solve it in the next session probably. Okay. So why we need to transfer the secondary parameters to primary side or primary parameters to secondary side, we will see step by step in the next session. Okay.